Hello students, so today we are going to learn about scalar and vector quantities in physics. So as here you can see that I have written the basic definition of scalar and vector quantities. That scalar quantities are those quantities which require only magnitude for their complete representation, and vector quantities are those which require direction also along with magnitude. So this is the basic difference between scalar and vector quantities, and we will try to understand this little more than this basic definition only. So let's start about scalar quantities. So scalar quantities, as I said before, these are the physical quantities which require only magnitude for their complete representation, and there is no role of direction. So there is no role of direction. So let us see by an example. So an example of a scalar quantity can be time. Very simple example. And suppose I ask you what is the time right now, and suppose you ask me or you ask me what is the time right now, and I say it is 5 p.m. Okay, so it is 5 p.m. and this is the magnitude, and it is completely self-explainable, and there is no need of direction here. That you won't ask me that in which direction the clock is kept, it is north, west, south, east, or upward or downward, it doesn't matter. So time is a quantity, physical quantity, which is completely defined by its magnitude only, and there is no role of direction. Similarly, you can consider another example of a scalar quantity like mass, and we can understand that suppose you are going to a shop and you ask the shopkeeper for weighing 1 kilogram sugar, and you ask him for 1 kilogram sugar, and the shopkeeper weighs 1 kilogram sugar on his weighing balance and he gives it to you. When he is weighing 1 kilogram sugar on his balance, it doesn't matter to you in which direction his weighing balance is kept. It doesn't matter in south, east, north, or west, in which direction the weighing balance is facing. So it won't matter to you. So mass is also a physical quantity where direction has no role into defining it completely. Like, so similarly you can have another quantity like suppose you say that when two cars met an accident unfortunately, and the first car was traveling with a speed of, suppose I say, 120 kilometer per hour. So it tells like this is the speed of the car, and you won't ask me when the cars are colliding in which direction the car was moving, like it is moving north, east, south. So it is just a description of an accident, and speed of the car 120 kilometer per hour, that is sufficient completely to tell the speed of the car. So speed is also a physical quantity where direction has no role. You won't ask me in which direction the car was traveling. So these are the three examples of scalar quantities which are completely defined by their magnitude only, and there is no role of direction. And I think you already know this, that in magnitude there are two things you can see here. In magnitude there are two things. One is the numerical value, another is the unit. And what is the relationship between numerical value and unit? Numerical value, suppose you write numerical value by n and unit by u, then the product of these two, numerical value and unit, that is constant. What does that mean? It means that if n is large, then u will be small, or if u is large, n will be small. So this means n will be constant divided by u, or you can write n is inversely proportional to unit. You can understand it by an example. Suppose I write 1 kilometer distance. This 1 kilometer distance can be written as 1000 meter, and further it can be written as 1000, and you put two more zeros, then it becomes centimeter. And similarly you can write it as 1000 and three more zeros, then it becomes millimeter, right? So you can see here that as you are moving from left to right here, so as you're moving from left to right, what is happening? The numerical value is increasing. So it was 1, then it became 1000, then it became 100,000, and like this. So numerical value is increasing, but you will notice that the corresponding unit is becoming smaller and smaller. So kilometer is the largest unit, meter is smaller than that, centimeter is further smaller, millimeter is the smallest unit. So as numerical value is increasing, the corresponding unit is decreasing. So numerical value and unit, these are the parts of magnitude representation. These two are inversely proportional to each other, and product of the n and u means numerical value and unit, that will remain constant. So if you are representing a same quantity, amount of quantity in two different units, then n1 u1, that will be equal to n2 u2. As here you can see 1 kilometer is equal to 1000 meter, both are equal, right? So n1 is the numerical value in first unit, u1 is the first unit, n2 is the numerical value in the second unit, u2 is the second unit. So this product will remain constant, and we will see it again in coming lectures that how we can use it into dimensional analysis. So I am leaving it here only. So let's come back to our definition of scalar and vector quantities. So I explained you that scalar quantities are those physical quantities which require only magnitude for their complete representation, and there is no role of direction into their representation. Now we come back to vector quantities. So what are vector quantities? So vector quantities are those physical quantities, as I have written here, they require direction also along with magnitude. Okay, so let's try to understand it by an example. So an example of vector quantity, very simple example is position. Okay, so suppose you have, this is your home on your map, suppose this is location of your home, and suppose this is the location of airport on map, and suppose someone asks you, someone is at your home, some guest has come and he asks you how to reach airport, and suppose airport is 20 kilometers from your home. So if you tell that person that you go 20 kilometers from your home and he will reach airport, so that's not possible because he can go into infinite directions, like 20 kilometers he can go in infinite number of directions and he will never reach to airport. So if he goes in this way, he goes in this way, he goes in this way, there are infinite number of directions he can go into, but he will never reach to airport. So for completely defining the position of the airport, you also need to tell him in which direction he has to move. So suppose this is the north and this is the direction east. Okay, let me draw it a little better. Yeah, suppose this is the direction east, and suppose this is the angle, you say suppose 75 degree I say, and you say that he has to move 20 kilometers 75 degree east of north, right? Then that person will be able to reach exactly at the airport. So you see here that 20 kilometer is the magnitude, and along with that you also need to tell the direction in which the person needs to move to reach at the airport. So position is such a quantity which requires direction also along with its magnitude for complete representation. Another example can be force. How? Suppose I say that there is some door which is locked and you need to apply some force to open that door. But suppose you are new and you don't know how to open the door, then you will ask me how to open the door. I will ask you, suppose I will ask you apply 10 Newton of force on that door and that door will get opened. But that's not complete, right? If you will apply 10 Newton force in some different direction, like in the closing direction, then the door is never going to open. I need to tell you that you have to apply 10 Newton force in the outward direction or in the opening direction. Only then this 10 Newton force will be completely defined. So force is a quantity which needs direction along with the magnitude. So 10 Newton here is the magnitude. 10 is the numerical value, Newton is the unit. Similarly here 20 kilometer, 20 was the numerical value and kilometer is the unit. So vector quantities require direction along with magnitude for their complete representation. So such kind of quantities are called vector quantities. So there can be further many examples you can have, like scalar and vector. So scalar quantities can be, like I told you, time, mass, speed. There can be work, pressure, energy. There can be many. And vector quantities can also be, there can be many vector quantities like velocity, acceleration, and force, torque, momentum, and impulse. There can be so many. So this was a brief introduction about scalar and vector quantities, and you also saw that how direction is needed for complete representation of vector quantities and how there is no direction role in the definition of scalar quantities. So I hope you understood scalar and vector quantities and you enjoyed this video also. So if you are enjoying my videos, keep watching and also suggest my videos to your friends, and also subscribe my channel for getting updates about new videos I am posting. So thank you very much, take care and bye bye.